And we are back into math. Here we are starting our final topic for the year. Topic 9, as you may see based on this number, is rational expressions and equations.
Whoop whoop!
Say what?
What?
Ow, my voice. In our first section, we're going to be talking about rational expressions, what they are, and then we'll be looking at how to simplify them. We've seen the word rational before. And we've seen rational numbers. Rational numbers are basically just like fractions. One number being divided by another number. When we're talking about rational expressions, they include rational numbers, but you could have variables too. So just as you have this fraction here, well, this thing that's a rational expression is also basically a fraction. But P and Q could be polynomials. So for example, 1 over x is a rational expression because this is a polynomial, this is a polynomial. That. Or something like 5x over x plus 2. Or if you really want to get crazy here, you could say like x cubed minus 4x squared plus 2x minus 9 over, 8x to the 4 plus 2x cubed plus 6. Woof! That meets the definition. You've got a polynomial being divided by a polynomial. Those are all rational expressions. Now the thing is, when we have those rational expressions, this bottom thing, the denominator if you will, cannot be 0. Just like when we have fractions we can't divide by 0, rational expressions, same. We can't divide by 0. So with rational expressions, if we have a variable in the denominator, we might have a non-permissible value. Or NPV. And if you want to find what the NPVs are for a particular rational expression, we just need to find out where the denominator is equal to 0. So in this first example, we're not even concerned with the x plus 3. That doesn't matter to us. But we are looking at this x minus 2. The question we're asking ourselves is what makes What makes x minus 2 equal to 0? That's what I'm asking myself there, because x minus 2 is the denominator. Well, if I want to find that out, I'm going to check what happens when x minus 2 is equal to 0. And if that's the case, then x equals 2. So it is bad for x to equal 2, because then the denominator is 0. You could state that the non-permissible value for x is 2, and a slightly different way of stating it is saying that there's a restriction, and that the restriction is that x can't equal 2.
All right. So, we're going to look at some more examples here. The next one we are going to look at is this one here. So we have 2 over x. And remember, when we're looking at non-permissible values, we don't really care about the numerator at all. All we care about is the denominator. And when will the denominator be equal to 0? Well, since the denominator is just x, it will be when x is equal to 0. So we can say that our NPV, or non-permissible value, is that x is equal to 0. Or we could just simply state x cannot equal to 0. So that one was nice and simple. This next one, as equally as nice. So again, when we're looking at our non-permissible values, we're only looking at our denominator. Our numerator means nothing to us. So when we're looking at our denominator, we are looking for when x minus 1 times x minus 2 is equal to 0. And if you could recall, back when we were doing solving by factoring, we noted that when we have two things multiply to give us 0, one of those things must equal 0. So we kind of broke it up into two pieces. We said, well, x minus 1 is equal to 0, or x minus 2 is equal to 0, which means x would equal to 1 here, or x would equal to 2 here. So, to get a denominator in which is equal to 0, that would be when x is equal to 1, because that would make this first piece equal to 0, and 0 times anything else will give us 0. And when x is 2, the second thing will equal to 0. And again, something times 0 will give us 0 in the denominator. So we would say that our NPVs would be when x is equal to 1 or 2, or we could just simply state x cannot be 1 or 2. All right. This guy here. Whoo, baby. Again, don't care about the numerator. Means nothing to us. But our denominator we do care about. And when we're looking for non-permissible values, it might be hard for us to say like, oh, hey, I don't quite know when that denominator is going to be 0. What will help us is if we actually factor that denominator. And we know how to factor this. In fact, we can see that there's just a GCF that we could pull out. Both terms have an x, so if we pull an x out of it, we will be left with x plus 1. Right, so why don't we rewrite this whole thing here to show us a different way of expressing that rational expression. So here we have written the exact same thing. It's equal. We haven't changed anything. We've just factored it so it represents the denominator in a little bit of a different way. And same idea. If our denominator was 0 here, that could happen if x is equal to 0. Or that can happen if x is equal to negative 1. Right? Because both of those values of x would give us a denominator of 0. So we could say that our NPVs are x is equal to 0 or negative 1, or we could just simply state x cannot equal 0 or negative 1.
We'll be continuing that with these next two examples. Don't forget that you can always do that thing where you just try things, you pause this video, you fast forward, you rewind, I don't know. But try out the examples, the next couple ones, see if you can do them, and then once you're ready, and I switch to the color I actually wanted, boom. Then press play. Ooh. Are we going to do this? It's because the variables are. See. Anyways. Alright, let's rewrite this thing. I think, how would I factor the top? If I were to factor the top, I wouldn't. I don't care about the top. It doesn't matter to me if I'm asked to find NPVs. This is useless. But that bottom, that can be factored. That's what something we care about. So, we do that. That's the bottom factored. And this gives us two options. How did you color code your whole life here? Ah, yes, a little underline and a little thing.
Oh, I just switched up a little bit each question, to be honest.
This is going to give us an option. And that's going to give us an option. And if r minus 4 is equal to 0, then r is equal to 4. If r plus 2 is equal to 0, then r is equal to negative 2. Which tells us then that we have restrictions that r cannot be 4 or negative 2. One thing worth pointing out, this order here doesn't really matter. If you say r doesn't equal negative 2 or 4, that means the same thing. It's like if your parents tell you you can't have any candy and you can't have any chips. It's the same thing as saying you can't have any chips and you can't have any candy. You just don't have either of them. I'm not even talking to you, Siri. That's ridiculous. And last example. Ooh, I could factor that top. But I won't, because it doesn't matter to me. I will factor the bottom as a difference of squares. And again saying if either factor is 0, then the whole thing collapses. If t plus 1 is 0, then t is negative 1. If t minus 1 is 0,
it'd be a good thing to point out that at this stage, this is not your final answer. So yes, you did technically solve for t to make the denominator equal to 0, but you can't just leave it as such. You need to either write NPVs, where t is equal to negative 1 and t is equal to 1, or you have to write the restriction that t cannot equal negative or positive 1.
Yeah, that's an excellent point. Thank you.
Alrighty. So far we've been crushing the NPV life, and that's actually not all we do when we're talking about rational expressions. Sometimes it might be useful to simplify rational expressions. And in doing so, what we actually are going to look at is how to make these rational expressions equivalent. Okay? So if we think back to things like fractions, something like 9/12, that can be rewritten in different forms. So we can rewrite it as 3/4, we can rewrite it as 18/24. The key here is that when we rewrite it, we do the exact same thing to the top and to the bottom with multiplication, right? So here, or division 2, that works. But to get from 9/12 to 3/4, we divided both the top and the bottom by 3. Or multiplied by 3. You could also think of it that way. To get from 9/12 to 18/24, we multiplied both the top and the bottom by 2. Life is A-OK. Similarly, we could do the same thing with rational expressions, even though there's variables involved. The one thing that we do need to keep in mind is that the NPVs in the original and modified expression. So as we are doing things to both the numerator and the denominator, we have to keep in mind those non-permissible values every single step of the way. Okay? So what we're going to be doing is we are going to be looking at these rational expressions, and we are going to be factoring them. Okay, and when we factor them, it breaks it up into factors, into multiplication statements. And when we see that, when there's multiplication, sometimes we could actually simplify the rational expression by crossing out factors that happen in both the numerator and the denominator, so we can eliminate those. So we are going to use factoring to see common factors of the numerator or the denominator that can be eliminated. Key point here. We can only eliminate factors. We cannot eliminate things that are attached by addition or subtraction. So if we have something that's like a +9 at the top, we have something that's like a +9 at the bottom, you can't be like, oh yeah, that's cool, just cancel out the +9s. No! We could only eliminate factors. So things that give us a multiplication statement. Alright, we're going to be doing some examples here, but I want to point out one little oopsie typo in 9.1.j. At the bottom there, I believe it was a 5n before. Could you please adjust that to be 8n? Thanks. Alright, so we're going to go through some examples. So in this example, or in these examples, we are going to be looking at simplifying these rational expressions, but we're also going to be stating those non-permissible values. Okay, so we're going to do both. I personally like simplifying the expressions first and then stating the NPVs at the end, because as you go through with that simplification, sometimes you factor then, or sometimes you introduce something that maybe wasn't quite obvious at the very beginning. So I like to state my NPV last. So this first example here, I am super lucky because the numerator and the denominator are both factored for me. Okay, so the numerator has a multiplication statement there. It has 2 times x minus 1. So the factors of the numerator are 2 and x plus 1. And then my denominator is also in factored form. We have the x plus 1 and the x plus 2 there. What I notice between the top and the bottom here, the numerator and the denominator, is they both have the factor of x plus 1. So what we can do is we can actually cancel them out. And what you could think about here is if I had a statement like 2 times 5 over... Actually, you know what? Even before we do that, we had like 10 over 24. I could rewrite that as 2 times 5 over 2 times 12. And the 2's can both cancel out to give me 5/12. Those are equivalent statements, right? Because if we cancel a factor out in both the numerator and the denominator, it doesn't change the value. So that is why everything is allowed here. So I'm going to get rid of this. But that is why we're able to cancel out the x plus 1 at the numerator and the denominator. So here, we would get our expression equal to be just a 2 on the top. And then we'd have x plus 2 at the bottom. To state the restrictions here, we would then just put a comma. And then we would look at the restrictions. So if I'm looking at this guy here, I need to look at my denominator at every single step. So even though my denominator of my final simplified expression just has the x plus 2, I know that I can't have x equal to negative 2. X cannot equal negative 2 because that would make this denominator here 0. But I also have to keep in mind the NPVs along the whole way. So if we think back to the very beginning here, we also had x plus 1 that was in the denominator. So I can't also have x be equal to negative 1 because that would also give me a non-permissible value. That would give me a 0 in the denominator at least at one point in this whole simplification process. So my final answer is a combination of two things. So I have my simplified expression, which is my 2 over x plus 2. I make a little comma here to indicate that there's a difference between my final expression and my restrictions. And then I state my restrictions last. So that's what your final answer should look like. It should be expression, comma, restrictions. Whew! That was kind of fun. Do you want to alternate back and forth?
Okay.
What do you want to do?
Cancel. Yeah. Next one. Very similar situation. We have an x that's on top and an x that's on the bottom, so they can eliminate each other. Oh, look, there's an x minus 4 and an x plus 4. Can they eliminate each other too?
No! Not a chance.
What? Why?
Because they're not the same factor.
Yeah. X minus 4 is not the same thing as x plus 4. They are different things, so they do not cancel each other out. But those x's, they are same. This x will eliminate this x. And that means that on top we're left with a 3 times x minus 4. And on the bottom, just x plus 4. And what we're saying is that these two expressions mean the same thing as long as x is not equal to negative 4 because of this, or 0 because of that. And I will put a box here. Oh, way to fail. Way to succeed.
All right. So taking a look at this next guy here, again, what we said at the beginning is we have to only eliminate things when there's factors, when there's a multiplication statement. So we can't go ahead and say, oh, there's a 9 at the top, oh, a 9 at the bottom, let's just cancel those guys out. That is not allowed because this is not a multiplication statement at the top and a multiplication statement at the bottom. In the same way, we can't go 5 plus 2 over 6 plus 2 and just cancel out, say, as 5 over 6. That is not true because that is not the same as 7 over 9. Right? So same kind of mentality is that we can only eliminate things if they are factors, which means there's a multiplication statement. Which means we've got to factor the top and we've got to factor the bottom. Luckily, take a look at this top guy here. Is that a perfect square trinomial I see?
Yes, it is.
Ooh, baby. So I've got t minus 3 and t minus 3. I'm going to write them out side by side when I do this, just in case I can cancel them out. But it's the same thing as if I had t minus 3 squared. Okay. My bottom here, ooh, that's a difference of squares. So I get t minus 3 and t plus 3. Okay. I am not done here. All I did was factor my numerator and my denominator. What I notice next is I have a common factor in my numerator and my denominator. I have a t minus 3 down there, and I have a t minus 3 up here. And I can't cancel out, I can't cross these guys out, because just like Mr. Athide said, these aren't the same because one's a t minus 3 and one's a t plus 3. So they have to be identical in order for them to cancel each other out. So here we are left with t minus 3 in the numerator and t plus 3 in the denominator. I, of course, have some restrictions going on. I know that because of this guy, t can't equal negative 3. But because of this guy, t also can't equal positive 3. So I could say t cannot equal plus or minus 3. Oh! And then I'll put a box around it because, ooh, so nice.
Quite nice.
Thank you.
And this next example, don't forget that there was an oopsie. So before this one, if you haven't changed already, make sure that's an 8. 4n squared plus 8n plus 3 in that denominator. Otherwise, everything will go awry. And just one thing, really. All right. So my first step here, I'm going to want to factor. I'm going to hope that the top factors. I'm going to hope that the bottom factors. Shaboom. And we'll probably get a 2n and an n here. And as I do some things and stuff in my head brains, I'll figure this out. We get that. In the denominator, we know that we could, like, are these going to be 2n and 2n? Or is it going to be 4n and n when you're attempting to factor? I'm going to kind of cheat and assume that one of these has to be a 2n. Just because I'm seeing this 2n here and maybe it's going to cancel. I don't know. If it doesn't work, we'll try the other thing. Anyways, I guess this has to be a 3 and a 1. And I guess they're all pluses. And if you expand, simplify that, you should get the original expression back. Well, that's all good and well. Here's my crossout color. Because there's a 2n plus 1 on top. There's a 2n plus 1 on the bottom. They have a common factor. So that's eliminated. On the top, I am left with n minus 3. On the bottom, I'm left with 2n plus 3. And again, we're not crossing these out just because there's a 3 on top and bottom. They are not glued to everything else with multiplication. This is subtraction. This is addition. That is not the time to eliminate things. But what I will do is specify when these expressions are equal. And they will be equal as long as n does not equal whatever makes this thing 0, which would be negative 3 halves, and whatever makes this thing 0, which would be negative 1 half. If you want, like if you want to process that mentally, you can do some side work to figure it out. And just go over to the side where you figure those things out and see what happens if 2n plus 3 equals 0, and what happens if 2n plus 1 equals 0. And then you can do all the business you need to do to work those out. And same for the other one. So you do have that option And I should probably indicate what my final answer is. It's this whole thing. Kablam.
Alrighty. Next example! Wow! Alright. So I am going to go ahead and start by factoring. And I'm going to factor the numerator. I'm going to factor the denominator. I'm going to assume both of them are factorable. But if I'm looking at this here, my a value, my numerator is 1. So I know I'm going to have an x and an x. Factors of negative 24 that add to 10. Well, that gives me like negative 2 and 12. Negative 2 plus 12. And the denominator here is another perfect square trinomial. So I have x minus 2 and x minus 2. Oh, baby. Alrighty. I'm looking at these guys and I notice that I have a common factor in my denominator here. It really doesn't matter which one I cancel out as long as I only cancel out one of them because there's only one in the numerator. So I'll cancel out this guy and this guy. And when I do that, my numerator is left with, I don't need a bracket anymore if that's it, x plus 12 and x minus 2 is in my denominator. We are stating that this original expression is equal to this final simplified expression as long as the following restrictions are met. If I'm looking at my denominator here, at any place in my denominator, I know that x can't be positive 2. And again, x can't be positive 2 there either, so I don't have to list it twice because it's the same number. So my final answer should be cease.
Good kid. Oh, right, there's one more example. It's over here. Step 1, cross everything out. Just kidding. Step 1 is still to factor. Oi. Oi. Uh-huh. So GCF on the bottom.
Perfect square trinomial on the top.
What? I'll take your word for it, but I'm not a mathematician. I'm just kidding, I actually am. I studied it a lot. Alright, there's my factored form of that same expression, which means that some things can get the boot. I will use blue as my cross-out color now. Now, I don't cross out both of these, just so we're clear. Just one. One from the top eliminates one from the bottom. Leaving us with 3x plus 5 over x. Aw, sick. Do you think I can just cross out these x's?
No!
Ah! Oh! Ow, my ear.
You shouldn't have crossed out those x's.
Why not?
Because they're not representing factors of the top and factors of the bottom.
So what we're saying there is if we want to cross out an x from this term and cross out an x from this term, we have to cross out an x from this term, but it doesn't have an x to give, so we can't do it. Instead, we just go ahead and state our NPVs here, our restrictions. So these expressions are all the same as long as x is not equal to 0 because of this guy. And then because of this other one, negative, oops, try again, 5/3. And no, bing, bang, boom. That's all for today's lesson.
Yeah. On the next page or next couple pages, there's some practice work that you can be doing. So please give it all a try. The answers are available at the end. So if you want to make sure that you're on the right track, that is there for you. Otherwise, that's all from us today. And adios, muchachos.
Peace. How do you stop this thing?